Hello again everyone, welcome back to ptet.chemistry channel. In this video, I will cover some terminologies of enthalpy changes as a prerequisite before I cover calculations on enthalpy changes that I'll feature in a couple of other videos. So you should have learned in school or by reading through your course textbooks, whatever course you're doing, they involve these enthalpy changes of formation. So enthalpy changes of formation are defined as the enthalpy change when you form 1 mole of the substance. So it's very important that you are forming 1 mole of the substance and you are forming it from its elements. So all the elements that form that substance, all meaning to say both the reactants and the products, all in their standard state. And if they are specifically for standard enthalpy change of formation, then you have to really specify under standard conditions. And the standard conditions are defined as 298 Kelvin, or you can say 25 degrees Celsius, and 1 atm pressure. So those are basic definitions again. I missed the part where I talked earlier about the enthalpy change when you do all that process, yeah? But the key thing really is form 1 mole of the substance from elements, all of them in standard states under standard conditions. All right. So it's given here the enthalpy change of formation of methane is represented by that. Methane is a gas at room temperature and pressure. It's formed from its element, which contain carbon as a solid, and also hydrogen as a molecular hydrogen. Okay. It has to be 1 mole here, but you have to balance the equation with the correct number of moles of the reactants. But it has to be 1 mole there. All of them are in their standard states under standard conditions. All right. So I'm sure you have learned this in school, but I'll just outline like what it means by the enthalpy change of formation by writing balance equation to show for it. Yeah. So for part A, sodium iodide is an ionic compound. It is formed from sodium, which is a metal. It's a solid at room temperature and pressure. It's formed from iodine, which is a molecule at room temperature and pressure. Iodine is a solid at 298 Kelvin, okay? And because I want to form 1 mole of it, of the NaI, where the formula given, it has to be Na plus and I minus because it's a group 17 halide ion. So what happened is I can halve this. Just like I can put a 2 in front of the reactant, I can halve it as well. Half times 2 equal to 1. I cannot change this to become NaI2 because that will give me the wrong representation, the wrong stoichiometric ratio of the mole ratio of the ions that react, because Na plus and I minus. And I cannot change the 2 in front because I want the enthalpy change of formation based on the definition that you will have known very well. You just need to act upon the definition. All of them are in their standard state. Don't forget the standard state iodine at room temperature and pressure. That will be further covered in group 17 chemistry. But you have covered under structure and bonding. When you compare the structure and bonding of chlorine, bromine, and iodine, we go from gaseous chlorine, liquid bromine, and solid iodine down the halogen group. Yeah, water. So when you have formation of water, there's liquid H2O, and then you form it from the hydrogen gas. That is at room temperature and pressure. You also form it from O2 gas. But again, you need a balance equation. It has to be 1 mole there. So there's 2 hydrogen atoms. It's balanced by 1 already. It's the oxygen that you need a half in front. And stat symbols are extremely important when you talk about enthalpy change of formation, as well as all the other enthalpy change. Yeah? The stat symbols govern the change itself. So you need to be very careful and be very careful on all that. Yeah? Carbon as a solid. Hydrogen as a gas is molecular, and O2 as a gas as well. It's molecular. Okay, so there are 2 carbon, so I have to have 2 carbon. I cannot put a number in front because I'm talking about enthalpy change of formation. I'm forming 1 mole of the substance from its elements, all of them in their standard state. So gas and gas there. The hydrogen, there are 6 hydrogen atoms on the right, so I need 3 H2 to get the 6 hydrogen atoms on the left. There's only 1 oxygen atom, so again, it's the half. So people coming in from GCSE or O-level, you might have been told off before for having fractions to balance equation, but really it does not make a difference. Yeah, again, this idea of when you have 2 there. 2 times half is 1. So you just need 1 oxygen atom on the left. And you cannot change that number there. You cannot change the number on the subscript. It has to be half there. So you gotta accept the fact that mole fraction, sorry, not mole fraction, fractions in these balance equations, it's just a ratio. It's just a number that you can divide by 2 or multiply by 2 throughout, okay? So it's equally acceptable even back in GCSE or O-level. It's just that some teachers don't like it. Personally, I really like fractions, yeah? Oh, sorry. You want to form 1 mole of the calcium carbonate. So forming 1 mole of the calcium carbonate from its element, so calcium, carbon, and oxygen. Alright, so calcium is a metal, it's a solid. Carbon exists as a solid, whether it's graphite or diamond, does not matter. And then gaseous there. So I have 1 calcium, 1 carbon, I need 3 oxygen. Again, 3 over 2 times 2 now. 3 over 2 times 2 is 3 oxygen atoms on the left. That balance the 3 oxygen atoms on the right. I got all my stat symbols in their standard states. Alright, NaClO3 solid is formed from its element. Sodium is a metal. It's formed from its element. Chlorine is a gas at room temperature and pressure. O2 is a gas at room temperature and pressure. I need 3 over 2 and I need 1 over 2. 1 chlorine, so half times 2 is 1 chlorine. 3 over 2 times 2 is 3 oxygen. So I hope that makes sense there. It again brings out the definition over and over and over again. Okay, those are basically 3 marks and you got to be aware of all those little things. Enthalpy of combustion. So enthalpy of combustion. So without this thing, that is the standard conditions, but without it, it's just referring to enthalpy change of combustion. Anyway, I'm going to define a standard enthalpy change of formation combustion. So it's to do with enthalpy change, but what is the process? Okay, when 1 mole of the substance completely burns, okay, so you can use completely burns or burns completely, I guess, or you can use the completely combust in excess oxygen. It has to be excess oxygen so that you completely combust, okay, all in standard states, meaning to say both the reactants and the products all refer to both reactants and products in the standard states. Because I have this thing there that refer to standard conditions, just like before, there was 298 Kelvin and 1 atm pressure, 1 atmospheric pressure. Okay, so this is enthalpy change or combustion for ethane. Okay, whereas formation, you just want to form 1 mole of the substance from its elements, all in standard state under standard condition. Enthalpy change or combustion is to do with burning 1 mole of the substance in excess oxygen. Okay, all the reactants and products in standard state. It doesn't specify what the product is because you get CO2 when you burn something that has carbon, right? But when you don't burn something that has carbon, like things like, I don't know, things like all of this has carbon, so you are fine. But I can include a further one like sulfur, right? So I'm going to start with E first. Things like sulfur, when you burn in oxygen, you can get SO2. Okay, that is the first step in the contact process. Okay, there is burning 1 mole of sulfur, okay, in excess oxygen to give you the SO2. All right, you can immediately see the enthalpy of combustion of sulfur, that is burning 1 mole of sulfur, okay, in excess oxygen to give you, well, all of them in the standard states. The product there is not always defined as the same. That's why we don't define the product. We just say all the reactant and products are in standard state. So that reaction there refer to the combustion of sulfur, but it's also equal to the formation of SO2. I hope you can see why that is. When you form 1 mole of the SO2, you form it from its elements under standard, well, all of the reactant and product in standard states under standard conditions. So you can get an identity, okay, by knowing the equations. Okay, there are a couple more identity that I'll talk about later on, but I've just shown you one there to exemplify exactly that. You don't always get CO2. When you don't burn something with carbon, how can you get CO2? All right. Well, carbon specifically, as a solid, will burn in oxygen. You can burn diamond and you will still get CO2. You can combust graphite and you still get CO2, except that combustion of diamond is going to be the most expensive CO2 you will probably get, yeah? Okay. There are a couple of videos online where they combust diamond and they bubble the gas formed through lime water, which is a test for CO2, and it turns milky. So it confirmed that burning diamond, okay, at a very high temperature, it does give you CO2, all right? So this reaction burns 1 mole, combusts 1 mole of carbon, 1 mole of the substance, in excess oxygen, okay, all of them in standard state and conditions, okay, all the in standard states, and this was done under standard condition. So I can say that enthalpy of reaction is actually equal to the combustion. So the reaction is this, enthalpy change of the reaction is equal to the enthalpy of the combustion of carbon, because I'm burning 1 mole of the substance, all right, in excess oxygen. But I hope you can also see that that is equal to the formation of CO2. Why is that? Because I'm forming 1 mole of the substance from its element, all of them in standard states under standard condition. This is one of the first very important identity that you need to remember, okay? And when I say remember, I mean, you know the definition of combustion, as in the definition of enthalpy change of combustion, definition of enthalpy change of formation, you should be able to get the identity fairly easily, okay? I'm going all over the place, but there are some important concepts I wish to cover here. I'll go straight to F first, which is hydrogen. So I've started with sulfur there, but I should have really started with something simpler. Hydrogen plus oxygen give you H2O. 1 mole of the substance burns in excess oxygen to give you that. Okay, so what do I get? Well, to balance the equation, I need 1 mole of the hydrogen, okay, because I want the combustion of the H2, you see. Delta HR is the combustion of the H2. And I forgot my stat symbol, which is very important. Gaseous hydrogen combined with gaseous oxygen to give me liquid water, because these are all in standard state, under standard condition, right? Assuming I'm talking about standard conditions, okay? So this reaction shows combusting or burning 1 mole of hydrogen in excess oxygen. So I need to balance the equation, but in reality it's excess oxygen. All of them in standard state under standard conditions. And I hope you can see that it's immediately equal to the formation of water, which was actually one of the examples shown earlier. There you go. Right, it's just that here we're talking about formation specifically. Now we're talking about the combustion of hydrogen, and you can immediately see the relationship between this again. So this is another relationship that is highly important, because whenever they give you examples of hydrocarbon combustion, it's always related to carbon and hydrogen, right? So it's important to know that the combustion of carbon is the same as formation of CO2. The combustion of hydrogen is the same as formation of H2O, as in the values are exactly identical. When they give you this, it could also be implied that they actually give you this. When they give you this, it could also be implied that they actually give you that, and vice versa, of course, yeah? Meaning to say that when I say you need to know the identity, you kind of need to know how to write equations based on definitions, and you should be able to get the identity easily. All right, so there are a couple of other examples here which you can practice on your own. I will write B for you, and then I won't go through the rest, I guess. So CH4 plus O2. So CH4 is methane. When you react with excess oxygen, it reacts with O2. It will give you CO2 plus H2O. So there's liquid and there's gas. I have to balance my equation always. 4 hydrogen, so I need a 2 in front of the water. I have 2 oxygen and 2 oxygen, so I need 4 oxygen altogether. I can have 2 times 2, that will give me 4, okay? So that is combusting 1 mole of the substance in excess oxygen, all of them in their standard state under standard conditions, all right? There's no specific identity like this that you can derive here, because here you're forming 2 substances, so it's not exactly like here where you're just forming 1 substance, and therefore I can relate it to formation. If there's one thing you need to know about formation and combustion, is also that the enthalpy of formation of any elements, okay, we're talking about elements in standard state. So what does the formation of elements mean? It means you're forming the element from the element, right? From the definition, forming 1 mole of the substance from its element. If I talk about the formation of the element, I'm forming the element from the element. That's why the standard enthalpy change of formation element is always 0, based on the definition. You're forming the elements from the elements. There's no change at all because you're forming elements in standard state from the element in standard state. Okay? The same thing with combustion is that I'm running out of space, but I'll find a space to write, is that the enthalpy change of combustion of oxygen is always 0. Again, it's down to the definition. You are burning oxygen in oxygen. So oxygen itself is not flammable, yeah? In case you don't know it, oxygen is not flammable. Okay, oxygen is not a flammable substance. A flammable substance means it combusts in oxygen. But oxygen itself is not flammable. You need to be aware of that. So oxygen combusts in oxygen. It's still going to be oxygen because it's not flammable, yeah? So that's why it's 0 enthalpy change, because it's oxygen plus oxygen giving you oxygen again, which is still O2, yeah? Okay, so those are the common identity there. I'll go through a couple other examples where we think about why certain things are wrong and why certain things are correct. So these are multiple choice questions. They're not the easiest in the world because they're designed to confuse students like yourself in terms of whether you know the definitions, are you aware of the stat symbols and stuff, yeah? So we want to think about enthalpy change of formation and which one is correct, okay? Here you are forming two substances. When you form two substances, enthalpy of formation is specifically to the enthalpy change when you form 1 mole of that substance only. So you can tell A is definitely wrong, okay? And then the other one is C is definitely wrong because aqueous would mean mixture. Aqueous mean in water. In fact, they show you, right? When you dissolve things in water, you get a mixture where the Na plus is surrounded by water and the Cl minus is surrounded by water. It is not enthalpy change of formation because you are not forming 1 mole of that substance, yeah, from its element. These are not element. Okay. The other thing is the definition. Forming 1 mole of the substance. Here you are forming 2 mole, and moreover, this is not an element. This is not element. This is actually a correct option. KMnO4 is your manganate plus 7, manganate 7. You use it as an oxidizing agent, and just like any exam questions, they can start off very easily by asking you to define. Instead of going to the redox straight away, they can ask you something on enthalpy change. Why not, right? And then we know that from its element in standard state, transition metal, main group metal, sorry, not main group metal, group 1 metal, okay, forming 1 more of that substance. So next bit, formation of propane. So propane is a gas at room temperature and pressure. And how would you know that? Okay, this is 3 carbon. I hope you know that the gas canister used in camping. So those gas canister used in camping, they often call it butane cylinder. Butane cylinder or butane propellant or whatever. That is already a compressed gas. So this one is 3 carbon. It has shorter carbon chain length than butane. It has weaker van der Waals forces between these 3 carbon propane, and therefore it has to be a gas as well. It's just by knowledge really, okay? So it's not a liquid at room temperature and pressure, okay? So you form it from its elements. If without the multiple choice option, you would just write from scratch. It formed from the carbon. It formed from H2, which is how hydrogen exists as an element. It's a gas, it's a solid, and you have to balance the equation with 3 carbon and 4 hydrogen molecule because 4 times 2 is 8, and that gives us A as the correct option. Is that correct? No, A is not correct because that is a gas. Okay, you see how multiple choice can be tricky sometimes? This is not a molecule. Has to be C there. Okay? But you're able to do it because you're able to do it in a structured question, meaning to say a multiple choice question shouldn't. I say shouldn't, doesn't mean that it won't, because it's very easy to make mistakes here and there, and it's easier to score a theory paper than multiple choice paper, okay? Because people tend to be very confident in multiple choice question when they should be working out what is the correct answer rather than what they think is the correct answer, yeah? Okay? Next thing, we talked earlier about this specific reaction where it is very specific. So really we are just looking at we're just looking at the combustion of H2 as well as the formation of H2O, okay? We know this is a specific identity. And then in terms of the value of X, you know this is the combustion. You know it's combustion of hydrogen. And enthalpy of combustion, if you just look at that itself, the enthalpy of combustion is always exothermic. Okay, that's how you know it's negative straight away without even thinking about the formation. But we know it's equal to the formation because of the identity that I talked in earlier examples. Alright, in this next example, it's specifically about atomization. So we are forming, is the enthalpy change when you form 1 mole of gaseous atom, okay, from its element in standard state. Okay, so it is the enthalpy change when you form 1 mole of gaseous atom. So when you form 2 mole of gaseous atoms, you know the definition is wrong. Okay, but in terms of from its element in standard state is very important. That's why they like to ask you chlorine, bromine, and iodine, because that is a gas at room temperature and pressure. There's a liquid that is a solid, not a gas, at room temperature and pressure. When you talk about the atomization, you are forming chlorine gaseous atom, bromine gaseous atom, iodine gaseous atom, and you're forming 1 mole, and 1 mole, which we don't usually write, okay? And therefore, they must have half and half and half. In this particular question, they're asking you on bromine, so bromine gas is wrong there. Bromine is a liquid at room temperature and pressure. This is part of your group 17, or you call it group 7, whichever curriculum board you're doing. You have done this back in GCSE or back in your GCE or level, yeah? Okay, so it's all down to definition. So as I mentioned before, the iodine is basically we are looking at forming 1 mole of gaseous atom from its element in standard state. Iodine is a solid at room temperature and pressure, and we cannot change that 1 there because by definition that is what atomization is, forming 1 mole of gaseous atom. Therefore I put a half in front. Okay, so this is not a question of the chlorine, but the chlorine would be from gaseous chlorine to gaseous chlorine atom, yeah? Anyway, so this is the last questions in these ideas on chemical energetics, just very briefly. Again, it's on enthalpy change or atomization. So what do we understand? We want to form 1 mole of gaseous atom from its element in standard state. I have to balance my equation. But because both of these are gas and gas, you will see later on that I can relate that to bond energy. Bond energy, bond dissociation energy. So we can say that is enthalpy change or atomization of hydrogen. But what are you doing? You have H and H bond. These are in gaseous state. And then you just have H atoms. Alright? So you also have the idea of bond energy, where you can form that, where you have H2, which is H and H, gas into gas. Bond energy, bond, well, some books will call it bond dissociation energy, or you could just think about it as bond energy. It's the energy required to break, okay? Energy required is always required, okay? You always require energy to break bond. What are we breaking? We break 1 mole of covalent bond, okay? To break 1 mole of covalent bond into gaseous atoms. Okay, to break 1 mole of covalent bond in gaseous state, no, 1 mole of covalent bond into gaseous atom. But I think I must be missing something in my definitions. I know that it has got something to do with both of these must be in gaseous state. You can only use bond energy in the calculations when you're talking about gaseous phase reaction. Your reactant and your product have to be in gaseous state, yeah? So maybe I should say break it into atoms. All reactant and product in gaseous state. Okay, I'm sure you have learned this in your definitions bond energy. You see how these and these are related? This is the multiple of 2. So what can we see the relationship here is that it's very important. The first reaction you see there is the atomization of H, because the atomizing, forming one mole of a gaseous atom from its element in standard state, it so happened that both are in gaseous state and both of these are in gaseous state. Therefore, it's exactly the multiple of 2. So meaning 2 times that, 2 times the first equation, equal to the second equation, which is the bond energy of HH covalent bond. 1 mole of that covalent bond is broken to form the gaseous atoms, both the reactant and the product in gaseous state. Alright, so this is energy required, this is energy required as well. So you cannot have a minus there, okay? It has to be both of them are endothermic, they require energy. Okay, so the enthalpy change atomization of hydrogen is therefore, so you just want that, so I can move the 2 to the other side. Because this is multiple, when I move to the other side, it becomes half the bond energy. Okay, this concept is extremely important when you go to do like a Born-Haber cycle. There's this thing called Born-Haber cycle. Is to work out the lattice energy of an ionic compound. Mostly done in A2 curriculum, either whether you're doing Cambridge International or some other curriculum, but that will become very important later on. Alright, so if you enjoyed this video, please subscribe to the channel and watch out for the other calculation videos where I'll use bond energy, where I'll use a mixture of enthalpy changes of formation and combustion. They will supplement whatever I cover in this video. It's mostly qualitative without any calculations so far. Okay, I'll see you in the next video. Thank you for watching.